Light sensors and how to use them. First, there are different kind of light sensors, and let me begin by showing them to you one after the other. First, we have the solar cells. Solar cells convert energy directly into electrical energy, and when light hits the solar panel or when light hits the cell, it generates a voltage and current proportional to light intensity. So the amount of voltage and current it generates is proportional to how the intensity of the light. And it can act as both a light sensor and a power source, but it's less sensitive to small light changes. Let's go to the other kind of light sensor. You have the photoresistor. Yeah, this is how a photoresistor looks. A photoresistor changes its resistance based on the amount of light falling on it. So in a photoresistor, the resistance of the photoresistor changes in equal proportion with the amount of light that is falling on it. That means in bright light, its resistance decreases. In darkness, its resistance increases. And we can use a voltage divider to measure these changes. That's a photoresistor. Then you have the photodiode. Photodiodes generates a small current when light strikes its p-n junction. That is, when light falls on this photodiode, it generates a small current. The amount of current produced is directly proportional to the light intensity, and it is usually operated in reverse bias for better sensitivity. Reverse bias, take note of that. Photodiodes are operated in reverse bias. Then we have the phototransistor. Now they are similar. It's just that internally in their circuits, instead of a diode, it is replaced by a transistor. And in this case, the light is serving as a base for that transistor. So just like I said, a phototransistor works like a normal transistor, but light replaces the base current. So when light hits it, it allows more current to flow between the collector and the emitter, and yeah, to amplify light signal. So it's therefore more sensitive than normal photodiode. So those are the different kind of light sensors that we have. Now let's go ahead and practicalize the use of different light sensors. Okay, so don't forget we talk about voltage divider and all. Let's first use the solar cell. Solar cell. So I have my solar panel here as a light sensor. Now, some security lights use solar panel as their light sensor. The same solar panel that charges the internal battery is the same solar panel that serves as a light sensor to differentiate between day and night. Okay, so normally this solar panel should generate a voltage, and from here we see that the peak voltage for this solar panel is 5 volts, and we can make it higher just by changing the parameter here. But let's just stick with 5 volts. And the current is 100 milliampere. Number one, let's connect a meter, just like it is said that a solar panel can also be a power source. So let's connect a meter directly to it, and you will see that it's generating, a solar panel would normally generate an electric current. So let's connect this. And let's start simulation. Let's move this closer. You see 5 volts. Now, when I click on the solar panel, you see this dial came up, and this is for you to simulate the amount of sunlight that is shining on it. So if I reduce this, that means I'm also saying lesser sunlight. No, when I brought it down to 0, it means that it's totally dark. And if I bring it all the way up, it means that maybe the sun is at its highest peak. Now look at the voltage, 5.01 volts. When I begin to drop it, the voltage also on the meter begins to drop until it got to 0 volts. That's why solar panels don't work at night, because there's no light shining on it. Now, how can we use this solar panel as a sensor, as a light sensor? It's simple. Um, it's simple. Let's just do a little bit of. So let's design a simple security light here that only turns on when it is dark, right? That only turns on when it is dark. Of course, it will have a separate battery that will be powering it. So let's start. We will need transistors, and we use a simple light emitting diode as our security light. Transistor. Let's rotate this. We need some resistors. Do you remember this connection where I said you should always connect the base of a transistor to ground via a larger resistance? So I'm going to change this to 100K. Okay. So I said you're going to need a separate battery source, since we're using the solar panel as a sensor to sense when it is day or night. This is a 9-volt battery. There's no rechargeable battery in this simulation. But this is what we're going to do. We're going to make use of it as though we're using a rechargeable battery. Okay, normally, the LED is meant to be connected to in this manner. We can connect LED in this manner. So let's put the LED in between there. Let's see whether they have other kind of LEDs. Okay, let's just use this. I'll rotate it. Now flip it. Now, I want to show you something. If I connect my circuit like this is a simple transistor as a switch. If you remember, this is a simple transistor as a switch circuit where this base control circuit now is coming from a solar panel. And if there's a supply into the base from here, this transistor is meant to turn on this LED so that current flow from the collector to the emitter to ground in this circuit. Now, if I let's make it smaller. Okay, if I start the simulation and you see in daylight, this light is on. When night falls, the light is off. And that is not what we want to achieve. Do you get? That's not what we want to achieve. So now there's a characteristics of a transistor that I have not mentioned to you. Let's stop the simulation. Let's remove this LED from here and connect this directly. I'm going to attach a meter to that collector. The meter to measure the voltage at the collector when it is on. So this should go to ground. Oh. Let's change the color of this thing so that it can be more clear. Okay, that looks better. Now, when we start the simulation, this is when the transistor is on. At full brightness, the voltage between the transistor, the collector of the transistor and ground is almost like 0 volts. Do you know why? It's just as though there's no resistance across this transistor. Very low resistance. So the resistance is almost 0 and therefore there's no voltage drop across this transistor. So when a transistor is fully on, when an NPN transistor is fully on, the voltage at the collector is almost 0. So for this one, it's 9.535 millivolts. If we begin to reduce it, you see it's dropping, but it's not linear because the transistor is not operating at the linear range. So when you make it totally 0, total darkness, you see that the voltage at the collector of the transistor has risen up to a voltage that is almost equal to VCC. I mean the battery voltage, 9 volts. Do you see that? So when the transistor is off, what is happening here is that the resistance of the transistor to the current path has increased significantly. At this stage, the resistance between the collector and emitter can be reaching up in mega ohms, many mega ohms. So technically, current is not flowing to the ground anymore. What am I saying? When the transistor is off, the output voltage from this place is almost equal to the supply voltage. When the transistor is on, the output voltage is almost equal to 0. Do you get? So we can use that characteristics to create something that is called an inversion circuit. What did I call that? Inversion. So what we are trying to say is that if there's, for an NPN transistor, if there's base voltage entering into it, if there is voltage of 5 volts or 9 volts entering into the base of the transistor, the voltage at the collector will be 0. If there's no voltage, if it is 0 volts entering into the base of the transistor, the collector voltage will be I, or equal to the supply voltage. Let me make you understand that better. So what we are saying is this. There's something called logic. So if the base voltage VB and VC, collector voltage, if VB is high, collector voltage will be low. If VB is low, collector voltage will be high. This is true for an NPN transistor. Do you understand that? Now let's go back to our simulation. So now that means that we can tap from this output to another transistor. Just follow me closely. So I'm just withdrawing everything we have here. So I'll connect this one goes to ground. Then the transistor again, I think I can copy. The base of the transistor now goes to this resistor. This goes to ground. And now this is where our LED bulb will come to. Okay, now we've designed a simple security light setup that only turns on when it is dark and turns off when it is bright. Let's test this. So don't forget, once current flows in through the solar panel to the base of this transistor, the collector will be off. And once the collector is off, there's no voltage in the collector. The collector is off. So the output voltage here will be 0 volts, and 0 volts will enter into the base of this one. Thereby, this LED will not turn on. But when there's no voltage coming from the solar panel, that is when it is dark, the input voltage to the base will be 0, and the collector voltage will be I, which is also equal to 9 volts, and therefore this place will receive a supply of 9 volts into its base. Okay, the values of these resistors need to be 100k here, 10k here, and 470 ohms here. And that's that. Let's start simulation. Now look at our solar panel. It is bright. When it is bright, you see that the light emitting diode is off. But once it starts getting dark to total darkness, the light emitting diode is now on. Do you get that? Do you get that? Okay, let me add one final tip for you. Assuming you want to make this into a battery charger circuit. Let's say you want to let this solar panel recharge this battery when there is proper power, when there is brightness or sun. All you just have to do is to connect from the positive terminal of the solar panel, connect from here, and let it go to the battery. But albeit we cannot connect it now. We can't connect it straight up like this. We can't connect it straight up like this. Do you know why? If we do, it's like if we connect it like this, that means that the supply from the battery is also allowed to flow back to the solar panel when the solar panel is not powered up, when there's no sun. Do you understand? I will delete this. So I'll put a diode in between. In forward bias mode, I have to rotate this. So now, what this does is that once there's brightness, once there's power once there's sun, the current from the solar panel flows through here, through the diode, and goes through all these circuits and charges the battery. That means it powers the circuits. Albeit, you know that this light will not turn on because of this part. It also sends signal into the base of this transistor. So let's simulate this circuit and see. So you see, so presently this will be charging back the battery. Albeit, of course, this solar panel is 5 volts. You can't use a 5-volt solar panel to charge a 9-volt system, 9-volt battery. The solar panel has to be near around 12 volts or more, 12 volts thereabouts. So once I begin to drop the brightness, just like before, the light should come on. The light should come on. So this light can be your security light, a LED security light. Finally, before I close on this session, what if I want to control my normal light at home, my normal security light at home, the 220-volt light? How do we go about that? That's where we come to use relays. We use a relay there. So let's stop the simulation. I will shift this one a little bit backward. Let's shift this. Okay, let's go look for relay. Okay, so we have some relays here. SPST, DPDT, SPST means single pole, double pole. These are the most common kinds of relay you find in the market. So I can still leave the light emitting down there. Let's zoom in. Let's bring this one closer. Now in this relay, you will see some terminals at the terminals here. How do I know what to connect to? I look at this diagram here. When you buy a relay, in most cases, when you buy a relay, in most cases, you follow the diagram that is drawn on it to know where to connect to. Do you get that? For this relay, it means that look at this. This and these are the switching contacts. So this is a switching contact, this. Then look at it, it went like this. This is the common. This is the normally open, normally close, and this is normally open. Why this two is a coil for this relay. Do you get that? So let's see the characteristics of the relay. There are no special characteristics. According to this, we are told that this relay is going to be operated by a 24 volts DC. I wish we can change that. Or let's see. Let's pick another relay to see. Let's pick this relay. Okay, this is better. This is operated by 5 volts. Now, in this case, you see, look at this diagram. This is, in this place is one switch. This place is another switch. Do you get? So this is one, this place, this point is this point. This point is here. This point is here. And this point is here. So these two are the coil of the relay. By this 1, 2, 3, 4, 5, 6 are the contacts, the switching contact of the relay. So I'm going to use this relay to simulate a live, connecting to a live, maybe electric bulb that uses 220 volts. So let's zoom out back. I'm going to rotate it so the coil can face where the transistor is. Okay. Let's shift this one further away a little bit more. Now, this transistor can just drive this relay directly. Do you get? So there's a terminal here. I'm going to connect it to my transistor. Let's first connect it. This one goes to the positive. And this one goes to the transistor in this manner. There's no 220 volt source here. Let me search for AC source. There's no 220 volt source in this simulation. Oh no, what we can do is this. So let's go and connect. Let's get a bulb. Let's get a bulb. Use a light bulb. So we're going to use this light bulb for our normal light bulb. So I just need one, and I'm going to use another battery. I'm going to use another battery to simulate my AC source. Let's use this battery. I'm going to use another battery. Let's bring it around here. Don't forget, I'm using this battery to simulate my AC source. So let's assume that this minus is my neutral and this plus is my live. So in connecting, we connect the negative, the neutral, the neutral now. You should connect both of them to the common of the relay. That is, for this relay, this is the common here and here, according to the diagram. Do you get? According to the diagram, these places are the common. So here and here. Let's redraw this. Let's take it through. Let's bring it like this. Let's change the color. Let's make this one brown to signify a live wire, and let's make this one blue to signify neutral wire. Okay, so that's that. So like this, we've connected our power source to the common. Now to the load, which is our bulb. So look at this. Look at the relay diagram again. This is the common. This is the normally closed. That is, this place and this place is like the normally close of your AC, of your relay rather. That place is normally connected. It's connected. So if you put any load there, by the time what is it called now? The relay switches on. If you turn off the load instead. Do you get? If you turn off the load instead. So that means our load will be connected to be normally open. Normally open. So let's connect the bulb to this now. Let me shift it up. It's looking complex, right? Yeah, welcome on board. Let's change to brown wire for the live. And for the neutral, we use blue wire again. Blue. Okay, we've drawn with success. Now, before you power on these circuits, you can't directly connect a relay to your transistor in this manner. It will blow up your transistor. Do you know why? There's something called reverse current that's it's peculiar to coils. So in this relay, there's a coil in this relay. So when this coil is energized or power on, it draws in some currents. When power goes off immediately, it generates a reverse current that is sometimes many times higher than the supply voltage. So when that reverse current happens, it wants to flow back into this transistor. Sometimes it exceeds the rating of the transistor, and therefore it can blow up your transistor. So what we normally do is to add a diode in between in this manner. So let me bring my diode. So the diode must be in this manner. The positive side facing the cathode, facing the positive side, and the anode coming also to the color green. So in this manner. So when that reverse current wants to flow back into the transistor, this diode, you know the transistor is already off at that time. This diode creates a pathway for the current to flow. So the current just flows through the coil back like this until it dies off. So in that way, you can protect your switching device, which is the transistor in this case, when connecting a relay. All right, this circuit is already big and complex, but this is the first practical circuit we are building. Don't forget, this 9-volt battery is simulating your AC power supply. Do you get? So let's run this simulation and see how it behaves. Let's stop first. Let me see. There are no special. I don't know the voltage that is required by this bulb. Let's just assume it's 9 volts too. Okay, let's start simulation. And now everything is off. Once it gets dark, what happens? Let's see. Yeah, and the light is on. The bulb is on. So this is the same thing that will happen with your security lights. Once it gets dark, your security light comes on. Once it gets bright, your security light goes off. So this is a simple, the most simplest use of security, automatic security lights. Make your own circuit, practice this and let me see. And if you also want to build this in real life, let me also know so that I can guide you through. We'll put a stop here now. There are still more sensors when it comes to light sensors to be covered, but let's do it one video at a time. Thank you.